Hello and good day everyone. Welcome to topic of generalized correlation of gases that will be presented to you by Group 18. In history of development, the most important pioneer is Kenneth Sanborn Pitzer. He introduced a semi-empirical model to understand behavior of ions dissolved in water. The very first correlation is based on compressibility factor. However, it is not directly correlated to properties of solution, thus it cannot be extrapolated. However, in 1975, Bjorn-Ikli and Michael G. Kessler tabulated the value of Z0 and Z1 as function of temperature and pressure that is accurate only for non-polar and slightly polar gases, as data used is based on argon and krypton. Second virial coefficient were introduced in 1957, and Abbott equation that has function of temperature only later developed by Michael M. Abbott in 1975. The equation is applicable for nonpolar gases at low and moderate temperature. For third virial coefficient, its precise information are substantially less prevalent compared to the second coefficient. However, there is decent correlation based on research. Hassan Orbi and Yuan H. Vera presented expression of C0 and C1 as function of reduced temperature in 1983 on American Institute of Chemical Engineering journal.
Now we move on to the definition and theory related to generalized correlation for gases. This is the basis for the two-parameter theorem of corresponding states, which says that all fluids, when compared at the same reduced temperature and reduced pressure, have approximately the same compressibility factor, and all deviate from the ideal gas behavior to about the same degree. Now there is an improvement to this theory, which is the basic for three-parameter theorem of corresponding states. It states that all fluids have the same value of eccentric factor when compared at the same reduced temperature and reduced pressure, have about the same compressibility factor, and all deviate from ideal gas behavior to about the same degree.
Now we proceed to the equation. In Pitzer correlation for compressibility factor, the equations related are Z equals Z0 plus omega Z1, and PV equals to Z nRT since the gas is assumed as ideal gas. Z is the compressibility factor for fluids of nearly spherical molecules, omega is Pitzer's eccentric factor, and Z1 is the correct for non-spherical intermolecular forces. Omega is 0 when it is a simple fluid. Z0 and Z1 are the function of reduced temperature TR and reduced pressure PR. The table shown is used to find Z0 and Z1 of the fluid based on TR and PR given. In Pitzer correlation for second virial coefficient, the compressibility factor Z is found using the fourth equation. However, if it is quantum gases like hydrogen or other noble gases, temperature-dependent effective critical parameters like Tc, Pc, and Vc will be used in treatment of the correlation. In Pitzer correlation for third virial coefficient, the compressibility factor can be found using the fourth equation.
Calculation. This is an example of a calculation where we need to determine the molar volume of N210 and 510 Kelvin and 25 bar using ideal gas equation and generalized correlation of gases. For question A, the calculated molar volume of N210 is 1696.1 cm3 per mole. For question B, the calculated molar volume of N210 is 1480 cm3 per mole. Next, for question C, the calculated molar volume of N210 is 1419.7 cm3 per mole. Lastly, for question D, we need to find second viral coefficient B, third viral coefficient C, and compressibility factor Z. Thus, the calculated molar volume of N210 is 1485.1 cm3 per mole. In conclusion, the D solution showing that the volume B differs from the value in part C by about 0.38%. The experimental value of molar volume of N210 at 510 Kelvin and 25 bar is equal to 1480.7 cm3 per mole. Significantly, the results of part B, C, and D are in excellent agreement. As a result, we can conclude that generalized correlation of gases provide a good approximation to real N210 behavior.
So these are our sources that we use to complete our assignment. That's all from us. Thank you.